In this video, we'll be focusing on solving IB physics past problem about topic 6, circular motion and gravitation. So this is for HL student paper 1 question. A mass at the end of string is swung in a horizontal circle at an increasing speed until the string breaks. The subsequent path taken by the mass is a line along a radius of the circle, a horizontal circle, a curve in a horizontal plane, or a curve in a vertical plane. So to solve this problem, we need to draw a free body diagram first. So we know the spring, it provides a force of tension. And the ball also receives a force of gravity by Earth. So when the spring breaks, it's gonna lose its tension, right? So there's gonna be no tension here. All it has is the force of gravity. However, when the string breaks, because it's in circular motion, so it has a centripetal acceleration pointing to the center. And we know the velocity, the tangible velocity, is perpendicular to centripetal acceleration. So you're also going to have a tangible velocity when the string breaks, and the direction is pointing tangent to it. Right? So if here, in this point, it's going to be pointing out of your screen. And if in this point, it's going to point to the right. So I'm just going to draw in this direction since it's easy to draw. And for this, we can know the path taken, right? So it's going to be moving in the curve in the vertical direction, right? So D is the correct answer. I know here I draw the force of gravity, but to be more accurate, I should draw the gravitational acceleration by Earth, since this is also a vector quantity that relates to velocity. An object rotates in a horizontal circle when acted on by a centripetal force F. What is the centripetal force acting on an object when the radius of the circle doubles and the kinetic energy of the object is divided by 2? So centripetal force is equal to mass times velocity squared over radius. So when your radius doubles, right, your centripetal force is going to be divided by 2. However, when your kinetic energy changes, your velocity is also going to change. So initially, your kinetic energy is equal to 1/2 times mass times VI squared, and then your kinetic energy is divided by 2, and this is equal to 1/2 times mass times your final velocity. So your initial velocity square is gonna be equal to 2k over and for your final velocity square is gonna be equal to 1/4. Yeah. Oh, actually no. Then half cancel on both sides. So it's gonna be equal to k over m. So your velocity square is divided by 2. So if it is divided by 2, then your force is gonna be divided by 2 as well. So this is equal to mv squared over 4r. So from here to here, your centripetal force is divided by 4. So A is the answer. An object at the end of a wooden roll rotates in a vertical circle at a constant angular velocity. What is correct about the tension in the roll? So it is greatest when the object is in the bottom of the circle, halfway up in the circle, at the top of the circle, where the force remain unchanged. So to do this, you can draw a circle here. So we know in this point, it receives a force of gravity. At this point, it receives a force of tension, and here also tension, right? And here, the centripetal force is provided by normal force, and here is also provided by normal force. So we know that at the top, tension is plus gravity is equal to centripetal force. And on the bottom, so here is also a force of gravity. Tension minus gravity is equal to centripetal force. And on the right or left, your normal force is equal to your centripetal force. So from here we know that your tension is gonna be equal to centripetal force minus gravity. And here your tension is gonna be equal to centripetal force plus your gravity. And here it's just gonna be equal to centripetal force. Oh, sorry, here should be tension. Sorry guys, I made a mistake. So here's tension is equal to your centripetal force. So from here we know at the bottom the tension must be greatest. Right. So A is the correct answer. The mass is suspended by a string from a fixed point. The mass evolves with constant speed along a circular path in the horizontal plane. The resultant force acting on the mass is what? So resultant force for an object in circular motion is just equal to its centripetal force. And centripetal force always points to the center of the circle. So C must be the answer. With acceleration of an object rotating with constant speed v in a circle of radius r. So this is very simple. Centripetal force, centripetal acceleration is equal to velocity squared divided by radius, and the direction is always towards the center of the circle. So B is the correct answer. A spherical planet of uniform density has 3 times the mass of Earth and twice the average radius. The magnitude of gravitational field strength at the surface of Earth is g. What is the gravitational field strength at the surface of the planet? So gravitational field strength at Earth is equal to capital G, so G constant times mass of Earth divided by its radius. And for gravitational field strength at the planet, for the planet, it's gonna be equal to G constant multiplied by its mass, which is 3 times the mass of Earth, divided by radius square. Sorry, here should be r square. And this is gonna be equal to 3 over 4 times G constant times the mass of Earth divided by r squared. And this part we know is equal to G is equal to gravitational field of Earth. So the answer is gonna be C. The maximum speed with which a car can take a radius turn of radius r is v. The maximum speed with which the same car under the same condition can take a circular turn of radius 2r is y. So initially centripetal force is equal to mass times its velocity squared over radius r, and now we know the radius has changed. So it's gonna be equal to mass times maximum velocity squared divided by 2r. So here, from its initial equation, we know that v is gonna be equal to centripetal force times its radius divided by mass, and then you take the square root. And now the v maximum velocity is gonna be equal to centripetal force multiplied by 2r divided by m. And this is gonna be equal to the square root of 2 multiplied by square root of centripetal force times radius divided by m. And here this part is equal to v. So the whole thing is gonna be equal to square root of 2 multiplied by v. So the answer is B. Which single condition enabled Newton's universal law of gravitation to be used to predict the force between Earth and Sun? So it gotta be point mass. This is the original statement of Newton's universal law of gravitation. So it predicts the gravitational force between two objects if and only if the two objects behave as point masses. On Mars, the gravitational field strength is about 1/4 of that on Earth. The mass of Earth is approximately 10 times that of Mars. What is the radius of Earth over radius of Mars? So we know that the gravitational field strength of Mars is equal to 1/4 of that on Earth. And now we can make equation by using this relationship here. So 4 multiplied by g constant times the mass of Mars divided by their radius square is gonna be equal to g constant times the mass of Earth, which is 10 times that of Mars. So 10 multiplied by sub Mars divided by radius of Earth square. And this is gonna cancel out on both sides. And this is also gonna cancel out. So now what we have is this 4 over radius square is equal to 10 over r sub Earth square. And from this we can solve for r sub Earth over r sub Mars is approximately equal to the square root of 10 over 4, which is equal to the square root of 5 over 2, which is approximately equal to 1.6. So C is the answer. The car moves at a constant speed around a horizontal circular track. The resultant force on the car is always equal to the force from the engine, the sideway friction between the tires and the track, the weight of the car, or is equal to 0. So we know the net force is gonna be equal to centripetal force, and centripetal force is being supplied by some sort of force, and in this case is supplied or provided by friction between the tires and the track. So B is the answer. The weight of an object of mass 1 kilogram at the surface of Mars is about 4 Newton. The radius of Mars is about half the radius of Earth. Which of the following is the best estimate of the ratio below? So mass of Mars over mass of Earth. So to solve this question is very similar to the previous question we have done. It's just we need to use proportionality. So 4 Newton here is equal to so the weight is equal to g constant times mass of Mars over its radius, right? And we know this because here is mass and here is weight. So we know that gravitational field strength is gonna be equal to 4 Newton divided by 1 kilogram, which is just equal to 4. Right? And for Earth, we know the gravitational field strength is approximately equal to 10. So 10 is equal to g constant times the mass of Earth divided by r Earth square. And we know the radius of Mars is about half of the radius of Earth. So I'm just gonna assume that the radius of Mars is r, and the radius of Earth is gonna be equal to, it's gonna be equal to 2r. So I'm gonna change this a little bit. Right. And now we can solve for the equation. So I'm just gonna use this. 4 divided by 10 is gonna be equal to G constant multiplied by mass of Mars divided by R squared multiplied by the reciprocal of this quantity here. And now we can cancel all stuff. So G constant cancels off. The R squared also cancels off. So this is equal to mass of Mars over mass of Earth times 4 is equal to, so this quantity here is equal to 4 over 10. So we know that the mass of Mars over the mass of Earth is gonna be equal to 1 over 10, which is approximately equal, which is equal to 0.1. So D is the answer. The center of two planets are separated by a distance r. The gravitational force between two planets is F. What will be the force between the planets when their separation increases to 3r? So when their separation is increased to 3r, their gravitational force is gonna be divided by 9. So this is A is the correct answer. And the reason why is because force of gravitational force is proportional to 1 over r squared, right? So Newton's universal law says this. The force of gravitation is equal to G constant times mass of object 1 times mass of object 2 divided by the distance between two objects. So when it becomes 3r, is going to be equal to G multiplied by M1 multiplied by F2, M2 divided by 9r squared. So we know the force is going to be divided by 9. A mass at point X gives rise to the gravitational field strength G at the point P as shown below. So here, the field strength is G. Identical masses play at point 1 as shown below. The resultant gravitational field strength on P is not Y. So here, the gravitational field strength is going to point to the left because the gravitational force by X is going to point to the left. And for Y, the gravitational force is going to point to the right. So the gravitational field strength is going to point to the right. So from this, we know that here, the field strength is going to be less than field strength here. So it's going to be less than G. So only C is the correct answer. A small sphere X of mass m is placed a distance d from point mass. The gravitational force on sphere X is 19 Newton. Sphere X is removed and a second sphere Y of mass 4m is placed a distance 3d from the same point. The gravitational force on the sphere is equal to what? So we know its mass is multiplied by 4, and the force of gravitation is equal to G constant times mass 1 times mass 2 over r squared. So when your mass is multiplied by 4, your gravitational force is also going to multiply by 4. And when your distance between two objects is multiplied by 3, your force is going to be divided by 9, right? This is because the r squared here. So if you plug everything in, it's going to be equal to G multiplied by 3 M1 M2 divided by 3r squared. Right. Wait, is the mass? Oh, sorry, the mass is multiplied by 4. And this is going to be equal to 4 over 9 multiplied by G M1 M2 over r squared. And this here, is equal to 19 Newton. So it's going to be equal to 4 over 9 multiplied by 19, which is equal to 40 Newton. So D is the answer. The gravitational field strength on the surface of Earth is G. Another planet has double radius of Earth. So we know their gravitational field strength is gonna be divided by 4, since gravitational field strength is equal to g constant multiplied by mass of Earth divided by radius, and its radius double, so it's gonna the r square is gonna be 4r squared, so their field strength is gonna be divided by 4, and has the same density of Earth. What is the gravitational field strength at the surface of the planet? So from here we know the radius is double, so their gravitational field strength is gonna be divided by 4. However, as their radius is changed, their volume is also gonna change, so their mass is gonna be changed. So we know mass of an object is equal to their density multiplied by their volume, and since their radius is multiplied by 2, their volume is gonna change as well. So it's gonna be 4 over 3 pi 2r cubic. So it's gonna be equal to 4 over 3 multiplied by r multiplied by pi multiplied by r cubic multiplied by 8. So here we know this is an object initial volume, and their volume here is multiplied by 8. So their mass is also gonna be multiplied by 8, right? And if their mass is multiplied by 8, their gravitational field strength is also gonna be multiplied by 8. So this is not equal to 2g. So C is the correct answer. Newton's law of gravitation is not equivalent to Newton's second law of motion. It explains the origin of gravitation, so it also does not explain the origin of gravitation. Instead, it is used to make prediction about gravitational force between two objects if the two objects behave like point masses. So C is the answer. For a particle moving at a constant speed in a horizontal circle, the work done by the centripetal force is equal to what? So work done is equal to change in kinetic energy, and since velocity remains constant, change in kinetic energy is going to be equal to 0, so D is equal to 0. An object of mass m at the end of the string r moved in a vertical circle at a constant angular speed omega. What's the tension in the string when an object is at the bottom of the circle? So here we have a force of tension. So here's the circle, and here's the string. So we know it receives a force of tension and a force of gravity by Earth. So T minus gravity is gonna be equal to their centripetal force, which is equal to times v squared over r. And we also know that velocity is equal to radius times omega. So this is gonna be equal to r times radius squared times omega squared divided by radius. So T minus mg is gonna be equal to mass times radius times omega squared. So tension is gonna be equal to gravity plus centripetal force, and we can factorize this. So it's gonna be equal to mass times the sum of g plus r times omega squared. So A is the answer. A spacecraft traveled away from Earth in a straight line with its motor shut down. At one instant, the speed of the spacecraft is 5.4 kilometers per second. After the time of 600 seconds, the speed is 5.1 kilometers per second. The average gravitational field strength acting on the spacecraft during this interval is equal to what? So we know gravitational field strength can be seen as gravitational acceleration. And acceleration is equal to final velocity minus initial velocity divided by change in time. So here it's going to be equal to 5.4 kilometers per second we can convert that to meter by multiply this quantity by 1,000. And minus is final velocity, which is 5.1. Oops, sorry, yes, 5.1 kilometer per second. So also multiply by 1,000 to convert the unit to meter and divided by time. So this is equal to 300 divided by 600, which is equal to 0.5, right? So C is the correct answer, right? Because this quantity is equal to 0.5. What is the definition of gravitational field strength at the point? So gravitational field strength is equal to force acting per unit of mass. So A is the answer. A body moves with uniform speed around a circle of radius r. The period of the motion is t. What is the speed of the body? So speed is equal to 2 pi r over t, where t stands for period of the motion and r is radius. So it's gonna be equal. So A is gonna be the answer. Planet X has mass m and radius r. Planet Y has mass 2m and radius 3r. The gravitational field strength at the surface of planet X is g. What is the gravitational field strength at the surface of Y? So you need to think about proportionality as well. So when your mass is multiplied by 2, your gravitational field strength is going to be multiplied by 2. And when your radius is multiplied by 3, your gravitational field strength is going to be divided by 9. So this is equal to 2 over 9 times g. So A is the answer. And if you don't see y, just plug in all of those quantities. So gy is going to be equal to g constant multiplied by 2m. So here I'm not going to write up m sub x here, just to avoid confusion. And it's over 3r squared. And this is equal to 2 over 9 multiplied by g constant multiplied by mass of planet X divided by r squared. And here this quantity here is just equal to g. The ball is tied to the string and rotated at a uniform speed in a vertical plane. The diagram shows the ball at its lowest position. Which arrow shows the direction of the net force acting on the ball? So when you see net force in a circular motion, you need to react immediately that net force is equal to centripetal force, and centripetal force always point to the center of the circle. So A is the correct answer. A planet has half of the mass and half of the radius of Earth. What is the gravitational field strength at the surface of the planet? The gravitational field strength at the surface of Earth is 10 Newton per kilogram. So gravitational field strength at Earth is equal to g constant multiplied by mass of Earth divided by radius squared, and this is equal to 10. And the planet has half the mass and half the radius, so it's going to be equal to g times mass of Earth divided by 2 multiplied by their radius divided by 2. And this is equal to I need to square your radius here. So this is going to be equal to 4 over 2 multiplied by g constant multiplied by mass of Earth divided by r squared. And here, this part here is equal to 10. So it's going to be equal to 2 multiplied by 10, which is equal to 20. So D is the correct answer. A satellite acts of mass and orbit the Earth with purity. What will be the orbital period of the satellites Y of mass 2, I'm occupying the same orbit as X. So occupying the same orbit means they both has a radius r, so their radius remain constant. Or to be more accurate, the distance between the planet, the distance between the satellite and Earth remain constant. So the distance is both r, and you need to find out how does your purity change. So centripetal force is equal to mass times velocity squared divided by r, right? And we can change this to times rate. So velocity is equal to radius times omega, right? So this is gonna be equal to r mass times radius times omega squared. But this doesn't really help because we need purity here. So velocity is also equal to 2 pi r over period. So this is going to be equal to mass times 4 pi squared r squared divided by t squared, and then here's another radius. So it's going to be equal to mass times 4 pi squared multiplied by r divided by t squared here. Right. So this is another derived formula for centripetal force here. And we need to know your period. So how do we solve this problem? So we also know that your period, your centripetal force is equal to gravitational force between two objects. So G satellite Earth divided by r squared is equal to v squared divided by so here is the mass of satellite. So I'm just gonna write to avoid confusion, since I'll also use here. So stand for the mass of satellite, m sub e stand for mass of Earth, and then we can cancel on both sides. And we know that here is equal to we derived the formula for centripetal force. So so let me rewrite everything. So here's gonna be gm1 gm satellite times mass of Earth. Oops, sorry. So I'm just gonna write times 4 pi squared multiplied by r over t squared, right? So now we can cancel out the mass here, and then we can solve for t. So t squared is gonna be equal to g constant multiplied by mass of Earth divided by 4 pi squared multiplied by r cubic. So to solve for purity, you're just gonna take the square root of this quantity. And this part here, g is a constant, mass of Earth is a constant, 4 pi r is a constant, and their radius remain constant. So purity is not gonna change. So it's still equal to t. An object of constant mass is tied to the end of a rope of length L and made to move in a horizontal circle. The speed of the object is increased until the rope breaks at velocity at speed v. The length of the rope is unchanged. At what other combination of the rope length and speed will the rope break? So the rope break when the centripetal force is equal to mass times v squared divided by L. And here for option A, your centripetal force is also going to be equal to 4v squared divided by 4L, which is equivalent to this quantity here. So A is the answer. So you can also calculate for B. So it's different. So it's equal to v squared over 2L. And for C is equal to mass times velocity square over 4. This is 4. This is 2. So this is A times L. And here this is also different. Right. So you can calculate this by yourself. A particle P is moving anti-clockwise with constant speed in a horizontal circle, which diagram correctly shows the direction of the velocity v and acceleration a of the particle in the position shown. So we know acceleration always points to the center, and velocity is always tangent to your centripetal acceleration. So we immediately know that A is wrong, D is wrong, B is wrong. So the only correct answer is C. The magnitude of the gravitational field strength at the surface of the planet of mass m and radius r is g. What is the magnitude of the gravitational field strength at the surface of the planet of mass 2m and radius 2r? So when your mass is multiplied by 2, your gravitational field strength is gonna multiply by 2, and when your radius is multiplied by 2, your gravitational field strength is gonna be divided by 4. So this is equal to g over 2. So this is B. So when you get familiar to this, you need to know immediately that for gravitational field strength, whatever your mass is multiplied by what factor or divided by what factor, your gravitational field strength is going to be multiplied or divided by the factor, and whatever your radius is multiplied or divided by what factor, and your gravitational field strength is going to be multiplied or divided by the square of that factor, right? So you need to know this, and if you don't see why, just list the equation. So initially G is equal to G constant multiplied by R divided by R squared, and then your mass is times 2. So Gm times 2 multiplied by 2, and then 2R squared. So this is gonna be equal to 2 over 4 times G times over R squared, right? And this part is equal to G. So your answer is B. What is the correct definition of gravitational field strength? So this is quite simple. You just need to know this. It's the force per unit mass acting on a small test mass. The horizontal disk rotates uniformly at a constant angular velocity about central x normal to the plane of the disk. Point x is a distance 2L from the center of the disk. Point y is a distance L from the center of the disk. Point y has a linear velocity v and the centripetal acceleration a. What is the linear speed and centripetal acceleration of point x? So we know they have the same angular velocity. So in velocity, your tangential velocity, your linear velocity is equal to your radius multiplied by your angular velocity. So for y, linear velocity y is equal to the distance between point y to the center of the circle, which is L, multiplied by angular velocity omega. And for x, it's just going to be equal to 2L multiplied by omega, which is equal to 2 multiplied by Vy, right? And for their centripetal acceleration, so I'm gonna row y here. Row v here since the question used v. And for centripetal acceleration of x is gonna be equal to velocity vx squared divided by 2L, which is equal to 2v squared divided by 2L. So it's going to be equal to 4v squared divided by 2L, which is equal to 2v squared over L. And for centripetal acceleration at point x is just going to be equal to v squared over L. So here is also equal to 2 times the centripetal acceleration of y. So B is the correct answer. The mass of Earth is me. its radius is r sub e. The magnitude of the gravitational field strength at the surface is g. The universal gravitational constant is g. The ratio of g over, the ratio of gravitational field strength over g constant is equal to 1. So g over g is equal to g times your mass sub e divided by re squared multiply by the g constant. Is this correct? So here's divided by g. Oh, sorry. So g should be placed here. Right, and now we can cancel the g constant. So it's equal to m sub e over re squared. So A is the correct answer. A communication satellite is moving at a constant speed in a circular orbit around Earth. At any given instant in time, the resultant force on the satellite is equal to 1. So resultant force, net force for circular motion is equal to centripetal force. Again, this is very important, and the direction is always pointing to the center of their orbit. So here 0 must be wrong, and here in this problem, your centripetal force is just equal to gravitational force on the satellite. So B is the correct answer. The mass of a planet is twice that of Earth. It has a radius half that of the radius Earth. The gravitational field strength at the surface of Earth is g. The gravitational field strength at the surface of the planet is equal to y. So when your radius is multiplied by 2, your gravitational field strength is going to be divided by 4, and your mass is multiplied by 2. So your mass is multiplied by 2, so the gravitational field strength is going to be multiplied by 2. So when your radius is half of the radius of r, then it's going to be multiplied by 4. So D is the correct answer. So you can also work this out by listing formula, right? So G is equal to this G constant. And then when your when your mass is multiplied by 2, is the G is multiplied by 2. And then your radius is divided by half. So this is equal to 2 multiplied by 4 multiplied by g constant multiplied by mass over r squared. And this is equal to A, this is equal to G. Alright, so one trick here. For gravitational field strength, if your radius is divided by n, then your g constant is gonna be multiplied by n squared. Sorry, it's gonna be divided by n squared. And when your radius is multiplied by n, your g is gonna be multiplied by n squared, right? So here is divided by the half. So the whole thing is gonna be divided by 1 over 4, which is equal to multiplied by 4, right? And a aircraft is flying at a constant speed in a horizontal circle. Which of the following diagram best illustrates the forces acting on the aircraft in the vertical plane? So there's gotta be a gravitational force, and you can immediately know A, B, C are wrong, because here is obviously this is a centripetal force. However, because centripetal force itself is not a force, it is a force provided by other force, and that's why it's a net force. So centripetal force shouldn't be drawn on your free body diagram. So D is the answer. pendulum bob is attached to a light string and is swing in the vertical plane. At the lowest point of the motion, the magnitude of the tension of the string is greater. It's definitely greater. So your centripetal force at the bottom is always greatest. And this is because at the bottom you receive a force of gravity and the tension, right? And T minus mg is equal to centripetal force. So T is equal to centripetal force plus gravity. So it's definitely greater than the weight of the mass of the pendulum ball. The car on a road follows a horizontal circular path at constant speed. Which of the following correctly identifies the origin and direction of the net force on the car? So centripetal force is provided by some other force. And that's why it is equal to the resultant force. So here, for car is provided by friction between car tires and road. So A and B are wrong, and the direction it always point towards the center of the circle. So D is correct. Two pulses are traveling towards each other. What is the possible pulse shape when the pulses overlap? So is A. This is very simple. Two satellites of mass m and 2m orbit a planet at the same orbit radius. If F is the force exerted on the radius of mass m by the planet, and A is the centripetal force, a centripetal acceleration of the satellite, what is the force and acceleration of the satellite with mass 2m? So they have the same orbit, meaning their radius remain constant. And for mass m is equal to mv squared divided by their radius r. So this is centripetal force for mass m. For 2m is going to be equal to 2 multiplied by m multiplied by v squared over r, right? So your centripetal force is multiplied by 2, right? So C and D are wrong. And your acceleration is going to remain constant, right? Since this part here remain constant. So A is the correct answer. A mass is attached to a string rotate in a gravitational field string with a constant period in a vertical plane. How do tension in the string and kinetic energy of the mass compare at P and Q? So we talked about this before. So tension at the bottom is always greatest. So tension at Q is greater than tension at P, because this tension here is equal to centripetal force plus gravitational force, right? And here, your tension is just equal to your centripetal force. So A is wrong, C is wrong. And what about your kinetic energy? So if we can use conservation of energy. So initial energy is equal to final energy. So your change in kinetic energy is equal to change in potential energy. To be more specific, change in your gravitational potential energy. Right? And for here, this is the lowest point, so I'm gonna have a potential energy of 0. So everything is kinetic energy. But for here, it has some potential energy and some kinetic energy. So kinetic energy at Q is greater than kinetic energy at P. So B is the answer. A cyclist rides around a circular track at a uniform speed. Which of the following correctly gives the net horizontal force on the cyclist at giving at any given instant of time. So your net force is always gonna be a non-zero quantity since it is equal to centripetal force, right? So if you're traveling in a circular track, there's gotta be a centripetal force, and centripetal force is equal to your net force. So A and B are wrong. Net horizontal force normal to the direction of the motion. So this is also gonna be equal. It is also gonna be a non-zero quantity because centripetal force is provided by some other force. Okay, so D is correct. The force F between particle in gravitational and electric field is related to a separation R of the particle by an equation of the form F is equal to A multiply BC over R squared. Which of the following identifies a unit for the quantity A, B, C for a gravitational field strength? So for B and C is kilogram. Right? So G constant multiplied by M1, M2 over R squared. And the unit for M1, M2 is all kilogram. And it has a unit of G, Newton here. So here is going to be equal to kilogram squared divided by R squared, so meter squared. So the unit for G is going to be equal to Newton times meter squared divided by kilogram squared. So D is the correct answer. So C is Coulomb. When you see Coulomb, you should immediately think about electricity and magnesium. An electron moves with uniform circular motion in a region of magnetic field, which diagram best shows the acceleration A and velocity V of the electron at given point P. A is definitely wrong because your velocity is always tangent to your centripetal acceleration. This is wrong because your acceleration always points to the center. This is also wrong. B is correct because your acceleration always points to the center of the circle, and your velocity is always tangent to your radius, or you can say is always tangent to your centripetal acceleration. Where's the problem? Oh, here. How many problems do we have? 2 more. Cool. A mass connected to one end of a rigid roll rotated at a constant speed in a vertical plane about the other end of the roll. The force exerted by the roll on the mass's way. So it's asking for tension here. Right? So tension. So tension is 0 everywhere. Obviously this is wrong. Constant in magnitude, this is also wrong. Because for example here tension is equal to centripetal force plus gravity. And here at the top, your tension is just equal to centripetal force, tension plus centripetal force. Since tension plus gravitational force is equal to your centripetal force. So tension is equal to mc minus mg. So your tension is not constant. Your tension is always directed towards the center, and maybe has and D says it has a minimum at the top of circular track. So this is correct, because at this point your tension is just gonna be equal to your centripetal force. So tension has a minimum value when at the top. And C says it's always directed towards the center. So this is not necessarily correct. So this statement is correct for centripetal force, but it's not necessarily correct for the force exerted by the roll on the mass, right? two particle x and y are attached to the surface of a horizontal mounted turntable. The turntable rotates uniformly about a vertical axis. The magnitude of the linear velocity of x is v, and the magnitude of acceleration is a. Which of the following correctly compares the magnitude of velocity y and the magnitude of acceleration y with v and a respectively? So for x, it has a velocity v and centripetal acceleration of a. So how do we do this problem? So we can see that x obviously has a closer distance to the central axis. And we know velocity is equal to the distance between two objects multiplied by their omega. And since they're on the same plane, they have the same angular velocity. So velocity at Vx is gonna be less than velocity at Vy, right? Because the distance here is greater. So A is wrong, C is wrong. And if the velocity is greater, then we can calculate their acceleration. So how do we do this? So you can solve this mathematically. So let's do this. Let's just say this is Lx, this is Ly. So V is equal to Lx multiplied by omega, and Vy is equal to L sub y multiplied by omega. And A is equal to V squared divided by Lx, right? And Ay is equal to Vy squared, which is equal to L sub y squared multiplied by omega squared divided by Ly, which is equal to Ly multiplied by omega. And A here is equal to Lx squared omega squared divided by Lx, which is equal to Lx divided by omega. And because Lx is less than Ly, so we know Lx multiplied by omega squared is always going to be less than Ly multiplied by omega squared. So which means that centripetal force, centripetal acceleration at point x is less than centripetal acceleration at point y. So D is correct.